NCRG002 Thermodynamic and Mass Energy Market Limits on Artificial Intelligence Scaling. A first principles derivation showing that continued scaling of AI and prospective super AI systems under the current design paradigm is bounded by physical and market constraints, and cannot proceed indefinitely without fundamental change to method. Author: Chris D. Seely, Independent Research QA/QC Analyst CWBII, Polymath. Framework: Recursive Partition Cosmology Working Group, companion note to prior RPC and near-extremal Kerr universe submissions. Document class: Falsification Digest, Popperian Status Taxonomy applied throughout. Status Taxonomy: Every claim in this paper is tagged with one of 5 statuses. Derived means the claim follows from established physics with no open dispute. Motivated means the claim is a reasonable structural inference supported by the derived physics and by observed data, but is not itself a law of nature. Confirmed means the claim is an empirical measurement or projection from a named authoritative source, subject to normal forecasting uncertainty. Outstanding means the claim is an open policy, engineering, or governance question that the physics does not resolve. Excluded means the claim has been evaluated and rejected as not applicable at current or projected scales, and is flagged so it cannot quietly re-enter the argument later. Abstract: This paper asks a narrow and falsifiable question. Given the thermodynamics of computation and the currently observed growth rate of the electrical and capital infrastructure supporting artificial intelligence, does the present design paradigm for AI and prospective super AI systems scale indefinitely, or does it approach a boundary condition that forces a change in method? The answer derived here is that it approaches a boundary condition. The boundary is not exotic. It is not set by information theoretic limits such as the Bekenstein bound, which this paper explicitly excludes as inapplicable at any scale under discussion. The boundary is set by ordinary thermodynamics of information erasure at the device level, combined with ordinary constraints on electrical generation, transmission, and capital formation at the civilizational level. The paper concludes that the current paradigm, defined here as brute force parameter and data scaling on von Neumann architectures cooled by rejection of waste heat to the environment, faces a closing gap between demand growth and physically achievable supply growth within this decade. And that continued progress towards super AI capability requires a change in computational method rather than a continuation of current scaling practice. Part 1. The Physics Floor. 1.1 Landauer's Principle, derived. Rolf Landauer showed in 1961 that erasing one bit of information in a physical system held at temperature T requires dissipation of at minimum an energy of K times T times the natural logarithm of 2, where K is the Boltzmann constant. This is not a claim about any particular technology. It is a claim about the thermodynamics of information itself. Any physical process that discards information, meaning any irreversible logical operation such as AND, OR, or a memory reset, must pay this energetic cost as heat released to its surroundings. This result was directly confirmed experimentally by Baroud and colleagues in Nature in 2012 using a colloidal particle held in an optical trap, closing the gap between the 1961 theoretical proposal and laboratory demonstration. 1.2 The resolution of Maxwell's demon, derived. James Clerk Maxwell's 1867 thought experiment proposed a demon that could sort fast and slow molecules through a partition without expending work, apparently violating the second law of thermodynamics by decreasing entropy at no energetic cost. The resolution, developed over a century through the work of Szilard, Brillouin, Bennett, and others, is that the demon's own memory must eventually be reset to perform further sorting operations, and that reset step is where the Landauer cost is paid. The demon does not defeat entropy. It defers the entropy cost from the sorting step to the erasure step. This is closed physics. 1.3 Present computational efficiency relative to the Landauer floor, confirmed. Modern semiconductor logic operates at roughly 1,000 to 100,000 times the Landauer minimum per logical operation, depending on process node, voltage scaling, and workload. This large gap between theoretical minimum and practical implementation is the entire reason that historical efficiency gains, driven by smaller transistors, lower operating voltages, and better architecture, have for decades been able to outpace growth in computational demand. It also means the floor is real but distant. There remains substantial room to improve efficiency within the current physical substrate before the Landauer limit itself becomes the binding constraint. 1.4 The Bekenstein bound, excluded as an active constraint. The Bekenstein bound sets an absolute upper limit on the entropy, and therefore the information content, that can be contained within a bounded region of space given a fixed total energy. It is derived from the combination of general relativity and quantum field theory and applies most directly to systems approaching black hole densities. No data center, no national grid, no planetary-scale computational infrastructure under construction or under serious proposal approaches the mass energy density at which the Bekenstein bound becomes physically relevant. This paper explicitly excludes the Bekenstein bound from the working derivation that follows. Any version of this argument that invokes Bekenstein as a live constraint on present or near-term AI scaling is making a category error and should be corrected. The active constraints below are ordinary heat transfer and ordinary electrical infrastructure limits, several orders of magnitude removed from Bekenstein territory. Part 2. The structural asymmetry. 2.1 The Maxwellian structure of present AI systems, motivated. A functioning daemon, in the resolved thermodynamic sense, requires three roles. There is the sorting operation, there is the memory that must eventually be erased, and there is the environment that absorbs the heat released at erasure. In present-day AI and platform systems, these three roles map cleanly onto three different parties. The sorting operation, meaning the extraction of usable signal from raw human behavioral, attentional, or biometric output, is performed largely by the population generating that output, often without full visibility into how the output is used. The value captured from that sorted signal accrues to the operator of the platform or model. The thermodynamic cost of the underlying computation, meaning the electricity generation, the cooling infrastructure, and the associated emissions, is absorbed by the electrical grid and its surrounding environment, which is to say by ratepayers and by the atmosphere. This three-way separation of labor, benefit, and cost is the structurally interesting feature of the present paradigm, independent of any single company or patent. It is motivated as a general description of the current industry, not proven as a universal law. 2.2 A documented instance of this pattern, motivated, textual claim confirmed. United States Patent Filing W02-020060606A1. Filed by Microsoft Technology Licensing in June 2019 and published by the World Intellectual Property Organization in March 2020. Describes a cryptocurrency system in which human body activity data, including brainwave or body heat emitted while a user performs a task such as viewing an advertisement or using an internet service, may be used to satisfy the proof of work condition of a mining process, explicitly framed so that a user may solve the computationally difficult problem unconsciously. The filing itself contains no reference to implants, coercive mechanisms, or any linkage to unrelated technologies, and no such claims are made about it here. It is presented solely as one specific, citable, textual instance of the general structural pattern described in section 2.1. Namely a formal design in which human behavioral or biometric output is substituted for computational proof of work, with the sorting labor performed by the user and the resulting value captured by the system operator. Readers should treat this as one documented data point supporting a broader claim, not as a singular mechanism unique to one filing. The same structural pattern is visible in ordinary engagement optimization systems, in reinforcement learning from human feedback pipelines, and in ordinary telemetry-based training data collection across the industry. Part 3. The Observed Growth Curve. 3.1 Global Data Center Electricity Demand, Confirmed, International Energy Agency, April 2026 Report. Global data center electricity consumption is measured at approximately 415 terawatt-hours in 2024. rising to approximately 485 terawatt-hours in 2025, a 17% year-over-year increase that outpaced the 3% growth rate of total global electricity demand in the same year. Electricity consumption specifically attributable to AI-focused data centers rose approximately 50% in 2025 alone. The International Energy Agency base case projects total data center electricity consumption reaching approximately 945 terawatt-hours by 2030 and approximately 1,200 to 1,300 terawatt-hours by 2035. 3.2 Regional concentration and structural strain, confirmed. In the United States, data centers are projected to consume more electricity by 2030 than the combined production of aluminium, steel, cement, chemicals, and all other energy-intensive manufacturing sectors together. Coal remains the single largest source of electricity supplying data centers worldwide at approximately 30% of the total, with the highest regional share found in China. Carbon dioxide emissions attributable to electricity generation for data centers are projected to peak near 320 megatons around 2030. Grid connection queues in many jurisdictions are already long, and the International Energy Agency estimates that approximately 20% of planned data center projects could face delay unless supply-side and transmission constraints are addressed. 3.3 Capital formation, confirmed. Capital expenditure by the largest technology companies on data center infrastructure exceeded $400 billion in 2025 and is projected to increase by a further 75% in 2026. The combined capital expenditure of 5 leading technology companies now exceeds total global investment in oil and natural gas production. This is not merely an energy story. It is simultaneously an unprecedented peacetime concentration of private capital formation directed at a single infrastructure category. 3.4 Efficiency gains and their limit, confirmed and motivated. Power consumption per individual AI task has been declining rapidly, at a rate described by the International Energy Agency as unprecedented in the history of energy systems, with improvements of at least an order of magnitude annually in recent years. This is the mechanism by which the gap described in Section 1.3 continues to be exploited. However, efficiency gains of this kind follow a logistic rather than an unbounded exponential curve in every historical precedent of process technology, semiconductor scaling included. It is motivated, though not yet definitively confirmed, that per-task efficiency gains will decelerate as the industry approaches the practical limits of current transistor and cooling technology. At which point the Landauer floor described in Section 1.3, while still distant in absolute terms, becomes the more relevant constraint on further gains, and demand growth driven by adoption and by more energy-intensive uses such as autonomous AI agents will dominate the net trend. Part 4. The derivation. 4.1 Statement of the core argument, motivated, built from sections 1 through 3, each individually derived or confirmed. Combine 3 established facts. First, the thermodynamic cost of information processing has a non-zero physical floor that current technology sits well above but is approaching in relative terms as adoption accelerates. Second, the electrical generation, transmission, and cooling infrastructure required to supply present-day AI computation is growing at 15 to 30% annually sector-wide and approximately 50% annually for AI-specific load, a rate that already outpaces total global electricity demand growth by a wide margin. Third, this growth is running against ordinary, well-understood limits of physical infrastructure construction, namely grid connection timelines, transmission capacity, generation build-out, and materials and critical mineral supply chains, none of which scale as quickly as capital can be deployed. The conclusion that follows is not that AI scaling will encounter an exotic physical wall such as the Bekenstein bound. It will not. The conclusion is the more mundane and more immediately actionable one, that a demand curve growing at 15 to 50% annually cannot be matched indefinitely by a supply curve, meaning new dispatchable and renewable generation plus new transmission capacity, that has historically required a decade or more to permit and construct in advanced economies. This is an economic and infrastructural derivation, built on physically confirmed inputs, not a claim of thermodynamic law being violated or approached in the strict sense. The mismatch between the rate of capital deployment and the rate of physical infrastructure construction is the actual, present, measurable boundary condition. It is already visible in rising grid connection queues, in the emergence of on-site natural gas generation as a stopgap at data center sites, and in regional capacity auction price spikes such as those observed in the PJM Virginia market. 4.2 Why brute force scaling under the current paradigm does not resolve this, motivated. The current dominant method for improving AI capability is scaling of model parameter count and training data volume on largely similar von Neumann architecture. Cooled by rejecting waste heat to the surrounding environment through air or liquid cooling systems that themselves consume a meaningful share of total facility power. Historically near 30% of total draw in less efficient facilities and closer to 7% in the most efficient hyperscale designs. Continuing to scale this method further requires continuing to scale electrical supply at a matching rate. Section 4.1 shows that this supply-side scaling faces construction and permitting limits that do not move at the speed of capital deployment. Therefore, continued capability improvement purely through this method of scaling faces a closing window. On a timescale of years rather than decades, unless one or more of the following changes occurs, each representing a genuine change in method rather than a continuation of current practice. A change in computational substrate, such as adoption of architectures operating closer to the Landauer floor, including reversible or adiabatic logic, or alternative substrates such as optical or analog computation for specific workloads, which could reclaim several orders of magnitude of the gap described in Section 1.3. A change in algorithmic approach, such as methods that achieve comparable capability gains with substantially reduced parameter counts or training compute, moving away from the assumption that capability scales primarily with raw compute applied. A change in energy sourcing and siting strategy, such as direct co-location with dedicated new generation, including advanced nuclear and geothermal sources already being pursued by the industry, which addresses the supply side of Section 4.1 without requiring a change in computational method, but does not by itself resolve the underlying inefficiency described in Section 1.3. A change in the growth trajectory itself, meaning a deliberate deceleration of demand growth relative to achievable supply growth, which is a policy and market choice rather than a technical one. 4.3 Falsifiable prediction. This paper makes the following falsifiable prediction, stated so that it can be checked against future data rather than treated as rhetorical. If the current paradigm of brute force parameter and data scaling continues without a change in computational method as described in Section 4.2, then data center electricity demand growth will either be forced below its recent 15 to 50% annual rate by supply-side constraints, evidenced by rising grid connection delay rates, increased reliance on on-site fossil generation as a stopgap, and sustained regional electricity price spikes in data center-dense markets, or capital expenditure growth in the sector will itself decelerate as financing costs and energy costs rise faster than realized returns on deployed compute. Either outcome is checkable against public IEA, grid operator, and hyperscaler capital expenditure data on a rolling basis over the remainder of this decade. If neither outcome is observed, meaning if demand growth continues unconstrained at current AI-specific rates through 2030 with no corresponding rise in delay, cost, or capital deceleration signals, this paper's central claim is falsified and should be withdrawn or revised. Part 5. Summary position. The physics that survives rigorous scrutiny in this paper is limited and specific. The Landauer bound is real and derived. The gap between present computation and that bound is real and confirmed, and it is large enough that it is not the near-term binding constraint. The Bekenstein bound is excluded outright as inapplicable at any scale presently under discussion, and should not appear in any future version of this argument as an active limit. The observed growth curve in electricity demand, capital expenditure, and infrastructural strain is confirmed from named current sources and is the actual, present, measurable boundary condition. The patent evidence is illegitimate. Narrow, textual data points supporting a broader structural claim about where sorting labor, value capture, and thermodynamic cost fall across different parties in the current industry, and should be cited as exactly that, no more and no less. The conclusion that present-day AI and any prospective super AI system cannot continue scaling indefinitely under the current design paradigm follows from ordinary infrastructural and economic limits interacting with ordinary thermodynamics. Not from any exotic or information-theoretic limit being approached. Continued progress toward more capable systems requires a genuine change in computational method, energy sourcing strategy, or growth trajectory, and the paper offers a specific, falsifiable prediction by which this claim can be tested against public data over the remainder of this decade. Correction log. This document supersedes the working thread discussion that preceded it. The following corrections were applied relative to earlier informal framing in that discussion. The Bekenstein bound was removed from the load-bearing argument and reclassified as excluded. All numerology-based readings of patent publication numbers were removed as unsupported by the patent text and are not part of this paper. The phrase runaway heat engine was retained only as a motivated structural description of an economic and infrastructural growth curve, and is explicitly not a claim of literal thermodynamic self-acceleration or violation of energy conservation. The term weaponizable was reframed as a governance and infrastructure concentration concern, outstanding as policy, and is explicitly not presented as a physical or supernatural claim. References: Landauer R., Irreversibility and Heat Generation in the Computing Process, IBM Journal of Research and Development, 1961. Barut A., Erekelian A., Petrosian A., Chiliberto S., Dylan Schneider R., Lutz E., Experimental Verification of Landauer's Principle Linking Information and Thermodynamics, Nature, 2012. Bekenstein J.D., A Universal Upper Bound on the Entropy-to-Energy Ratio for Bounded Systems, Physical Review D., 1981. Maxwell J.C., Theory of Heat, 1871, Discussion of the Sorting Demon Thought Experiment. World Intellectual Property Organization, WO 2020060606A1, Cryptocurrency System Using Body Activity Data, Microsoft Technology Licensing LLC, filed the 20th of June 2019, published the 26th of March 2020. International Energy Agency, Energy and AI, April 2025. International Energy Agency, Key Questions on Energy and AI, April 2026. International Energy Agency, Data Center Electricity Use Surged in 2025, even with tightening bottlenecks driving a scramble for solutions, April 2026. Brookings Institution, Global Energy Demands Within the AI Regulatory Landscape, April 2026 update. End of NCRG002.